Okay, triangles is our topic, and what we're learning applies to all geometrical polygons, but we're going to focus on triangles. But some of the concepts and ideas that I'm going to be sharing with you can apply to quadrilaterals or um, 10-sided figures, or those kinds of things. So a polygon with the what's a similar polygon? It's a polygon with the same shape, but maybe a different size. Okay, but it has to be the same shape. And what gives it its shape is angles that are congruent, and they got to be corresponding angles. So congruent, corresponding angles. We have two triangles here. Let's say the one on the left is smaller than the one on the right, as it appears. But if these were similar, they would need corresponding congruent angles. So this looks like a 90-degree angle. So let's say both those correspond. Maybe this is 40 degrees up here. This would be 40 degrees and maybe 50 here. And so we say triangle ABC and DEF are going to be similar because their angles are congruent. The side lengths don't have to be congruent, but the side lengths need to be proportional. And we'll talk about what we mean by proportional in a second here. I'm going to highlight a little bit here. So I want AB to correspond to DE. BC is going to correspond to EF. And AC is going to correspond to DF. And let me just put in some side lengths. So for ABC, across from the smallest angle, we'll put the smallest side, say 3, and then 4, and then 5. So we got this right triangle here with the side lengths. And you can move from one triangle to another. You can create a similar triangle through what we call a scale factor. And you may have built models like of an airplane or a car, and you may have heard about or read a map that's a kind of a scale of reality. And they always have these scale factors like, okay, this model that I'm creating is 1/60th of the real size, or that kind of thing, right? And so a scale factor is something that you would multiply all the side lengths by to create your new thing, or even the idea of a projection, right? I'm projecting what's on my computer screen here. So what you see is similar to what's here. It's the same shape, but it's a different size, right? And so there's some kind of scale factor that would relate what I'm looking at to what you're looking at, okay? So for example here, if I want my scale factor going from left to right to be 3, so then what I do is I'd multiply all these side lengths by 3, and this would be 12, this would be 9, this would be 15. And by scaling it, it creates proportionality. And so what I could do is I could say, well, if I look at my corresponding sides and I go, well, 4 corresponds with 12, and I could set that equal to any other, doesn't matter. If I look at the green, I could say, well, 5 is my smaller triangle, and that corresponds to 15. And if I reduce those fractions, I should get the same thing, which is 1/3 and 1/3, right? And it also works with the blue one. 3/9 also reduces to 1/3. So all of these reduce to 1 over the scale factor. Okay. if you look at, let me just talk about one thing here. Say we had a missing side. Say instead of 9, I put x here. We know it's 9, right? And to solve for x, there's a few ways we could do that. One, if you know the scale factor, it's really easy. Oh, 3 times the 3 is going to be 9, and I got it, right? But we'll come into some problems where the scale factor is not so obvious. God bless you. And what you can do to solve for x is to set up a proportion. So it'd be something like this. You say, well, x corresponds with the 3 is equal to, and then you have some choice, right? So I'm going to use the green. So what would I make it equal to? 5 over 15? Which one? Because it matters, huh? Should I do 5 over 15, or should it be equal to 15 over 5? Why? You got to keep it matched up. So we went larger over smaller, right, for x over 3. And so we're going to have to go larger over smaller, same direction, 15 over 5. Otherwise, you will end up with the wrong answer. And so that's part of my point here is setting up a proportion to solve for x is important in how you organize this. So 15 over 5. And when you have proportions and you're solving, a proportion is just one fraction equal to one fraction. That's what we mean when we say proportion. You could get, what we've learned before is get rid of the denominator, so we can multiply both sides by what? 3, right? And that gets rid of this one. So we have 15 times 3 over here. And then to get rid of the 5, we multiply both sides by 5, and it gets rid of the 5 over here. So we end up with 5x equals 3 times 15. And so instead of going through all those steps, what people tend to do is say, we could just cross multiply. 5 times x is equal to 3 times 15. It's a shortcut that works, and it only works when you have a proportion. When you have one fraction equal to one fraction. Where people start to mix this up is like if they're multiplying fractions, they're saying, let's cross multiply. You can't. No, you can't do that. It's only in this scenario when you have an equal sign between two fractions. Okay. In setting this up to solve, that's one way to set this up. I want you to set up another proportion using the same 4 parts that we used for this one. What's another proportion that would give us the same exact answer? What's that? So I want you to use the 3, the 5, the 15, and the x. Give me another proportion that would give me the same answer if I solve for x as this one. Maybe I'll suggest one. How about 3 over x is 15 over 5 over 15? If I cross multiply here, I get 5x equals 3 times 15, which is the same exact thing I'd have over here. But notice it's different how I set it up, right? I put small over big. There's another way with those same 4 things. What's another way? Give me another proportion with the same 4. Did it work out okay? Thanks. 5. I like how you're thinking, okay. Why can't we do 5 over x? So 5 over x 5 and x don't correspond with each other, right? And so we need to, instead of 5 over x, if we could put 5 over what? 5 over 15. Do we have that one? We do. We could also put 5 over something else. You could do 5 over 3. If we do 5 over 3, then we'd have 15 over x. What's happening here is we're not corresponding, but we're working within the same triangle. 5 and 3 come from the triangle on the left, 5 over 3, and then the corresponding sides would be 15 and x in the larger triangle. And notice when we cross multiply there, we end up with 5x equals 3 times 15, which again is the same exact thing we get with the other one. There's one more. 15 over x and 5 over 3, I'd count that as the same, it's just flipped around. 3 over 5 and x over 15. Again, if you cross multiply, you get 5x equals 3 times 15. So why am I doing this? I'm just wanting to show you that there are multiple ways to set up the same, to solve. There are 4 different proportions that end up with equivalent answers when you solve for x. There are a couple wrong ways too, and so just be careful. The first 2 that we did are when I set up that first fraction, it was with corresponding parts. X corresponded to 3, right? The last 2 fractions we did together, we did within the same triangle. 5 and 3 were in the same triangle, and then the second part would correspond. So just letting you know there's a variety of ways out there, and we're going to be using those kinds of things. Okay, let's look at number 1. If triangle, oh, sorry, one more thing to say here before we leave it. The notation. So when you say similar, so it's written this way. So triangle ABC is similar, which is kind of like the congruent symbol, but without the equal sign, right? We're just putting the little about part. So it's similar to triangle DEF. It matters the ordering of this. You know, the first one doesn't matter, but the second triangle that you write has to correspond. So A has to correspond with D, B has to correspond with E, C has to correspond with F. So the ordering that you write, that matters. And so that's the notation for similar. Okay. So if we look at number 1, we see that notation. Triangle JKL is similar to triangle PMN, which means what? What does it mean to be similar? Angles, corresponding angles are congruent. So angle J would be congruent with what? Angle P. Okay, they're not oriented the same way, but those are both the first letters, and so we could say angle J is congruent to angle P. Angle K would be congruent to which one? M, because those are both the second letters in the congruence or the similarity statement. And then angle L would be congruent to angle N. So we get congruent angles. These shapes do not look similar, so they are not drawn to scale at all. But we're going to still work with it. So that's one piece that we get. What else do we get? We get not congruent, but we get proportionality. So JK, that length, over which length in the second triangle? Let's do corresponding in this case. PM is going to be the same. That fraction will reduce to the same fraction as KL over what? MN, because KL are the last 2 letters in the first triangle, and then MN are the last 2 letters in the second one. Oh, I don't know why I did that, but I meant MN. And then also, there's one more fraction that will reduce to these. What is it? JL over PN. Okay. So this is what we mean by side lengths are proportional to each other. Look at number 2. So here I'm saying that the two triangles are proportional, and we need to solve for x and y. So what you want to do here is just be careful how you, what side's proportional to what. So like side y here is proportional to which, or GJ, okay, is proportional to which in the first triangle? EF. Okay. So EF we know is 2/3. We're not sure what y is. If we had the scale factor, then we could multiply that scale factor by 2/3 and get y, but there's nothing that indicates what the scale factor is either, right? How about DE, which we know is 9? What's that going to correspond with? HJ. Okay, so let's solve for y. So we don't want to, if we're solving for y, we don't want to involve the x's because that'll make it more complicated, right? So let's work with what I highlighted green and yellow, and let's set up a proportion to solve for y. And like I said, there's 4 different ways to set that up. How would you like to set it up? What over what equals what over what? Okay. So I heard 9 over 15. If we do 9 over 15, what does the second fraction have to be? 2/3 over y. Okay. And then we can cross multiply, and you get to choose which one you want to do first. I like the variable on the left side, so I'm going to do 9 times y first is equal to 15 times 2/3. And how do you multiply 15 times 2/3? 15 over 1. So 15 times 2 and 1 times 3, so it's 9y. It's 30 over 3, or 9y is 10. So y is 10 over 9. So we solve for y. So we want to now solve for x. Why don't you set up a proportion to help you solve for x and see if you can solve for x. So on this one, all right, so I'm going to set up a proportion. I'm going to go corresponding sides. I'll do blue over blue, right over left. So x squared plus 2x over x squared. And again, if you didn't set it exactly the way I'm doing here, it doesn't matter. What matters is when we both cross multiply, that we get the same thing. That's what matters, okay? So look at my second step and see if it matches your second step. And then I'm going to match this up with the green. So if I do this, what does my next fraction have to be? 15 over 9, good. So then I cross multiply and I get, I'm thinking ahead. I want the most of my x squares to be on the left, so I'm going to go 15 times x squared first. Equals 9 times, and careful here, if I have 2 terms, and that 9 has to be multiplied to both. You have to distribute to both. So I'm going to put the x squared and the 2x in parentheses so that I don't forget to multiply the 9 to both of them. Okay? And so we end up with 15x squared is equal to 9x squared plus 18x squared. Sorry, 18x. Okay. Then what? Can't factor yet. Factor is a good direction, and what's telling us about this problem that factoring is a way to go? X squared, right? If you have x squared, that's called quadratic. One method to solve quadratics is factoring, and that's the only method that we've studied yet. We'll learn more methods later, but that's all we know. Whereas when we were solving for y, factoring didn't trigger at all because there's no y squared. So it's the squared part that should trigger. I should factor. But before we factor, we need to make sure it's equal to 0. Okay. So I'm going to move everything on the right to the left side. So subtract 9x squared and subtract 18x from both sides. And we end up with 15x squared minus 9x squared is 6x squared minus 18x equals 0. And then we factor. And there are 5 different types of factoring that you need to know that we studied in Unit 2. And if you don't know what all 5 of those are, you need to have Unit 2 really close at hand so you can look back, okay, and get comfortable with that. So which of those 5 would apply to this one? So there's no perfect square. 18 is not a perfect square. There is a difference, and I'm glad you're seeing that, and there's 2 things, but it doesn't quite fit the difference of 2 squares. Okay, there's distributed property one, we call it the greatest common factor, but yes, you're right. So notice that you can factor out a 6x from both of these, and we're left with x minus 3. And so now it's factored. That's the easiest factoring, the factoring out of GCF, and you always want to look for that one first. Once it's factored, set your factors equal to 0, so 6x equals 0, and x minus 3 equals 0. And when you divide by 6, you get x is 0. When you add 3, you get x is 3. So you get 2 possible answers for x. If you have a context to your problem, and we do, we have triangles, then just make sure those answers make sense. Do both of those answers make sense? Which one doesn't make sense? X equals 0 doesn't make sense, particularly with either of them. If you plug it in, that makes the side length 0. And so that's why we can't have a triangle with a side length of 0. And so x equals 3 is what we keep. All right. Now some of you may have said, hey, you know what? I didn't factor, Mr. Martian. I got x equals 3. Anybody in that category? Okay. But I'm going to say this. You didn't get x equals 0, right? And if we didn't, most of the factoring where you guys are headed, solving quadratics won't have a context. And you'll be asked to solve something like this and find the answer. And if you just give 3, you'll be marked wrong. And so practice my way, because I know where you're headed, and I want you to be able to get both answers. Okay. All right. We're going to skip around a little bit. Your homework, by the way, is to, you're going to complete all this. So I'm not going to do it all with you. I'm going to do some of it with you to get you a good grasp of what we're doing. But you're going to finish what we don't finish together. Okay. So let's skip ahead to number 7. And by the way, I have an error on number 6, and so 6 is not going to be part of your homework or part of our notes until I can fix that, okay? All right, so let's look at number 7. We need to solve for x here. And they're telling us triangle JKL is similar to triangle MKN. And here's what I want you to do. I want you to set up a proportion that would help us solve for x. Go. Set up a proportion that would help you solve for x. And if you're sitting and waiting, after that, go ahead and cross multiply and just keep going. But I want everybody to set a proportion to solve for x. everybody have a proportion? At least that far. Okay. This shape, or this, like 7 and 8, these kinds of problems tend to be tricky in setting up proportions. When you set up proportions, make sure you're setting up a proportion of a side of a triangle with a side of a triangle, like the full side. And so there's one expression up here that doesn't represent a full side of a triangle. Which one is it? What is it? NL, which is x minus 2. That x minus 2 is not a full side length of a triangle. It's part of a side length of a triangle. It's not the full side length. So if you're using x minus 2 as a numerator or denominator in one of your fractions, you've messed up. Okay? So let me show you what I have. So I've highlighted corresponding sides. So with my small triangle, the green is 3x squared minus 1 and the 2, right? With the larger triangle, I have the x cubed plus x squared minus 1 as the base. And then here, I had to add the 2 with the x minus 2 to get that full side length, which is just x. And so x is that full side length that you want to use. And so when you set up your proportion, there's multiple ways to do this, but I'll do x over 2. So yellow to yellow is x cubed plus x squared minus 1 over 3x squared minus 1. And then I'm going to cross multiply. And I'm thinking which way I want to do this. I could go either way. But x cubed is my biggest power, and so I want to go 2 times that first. So 2 times the x cubed plus x squared minus 1 is equal to x times 3x squared minus 1. So after you may set up your proportion differently than me, because there's 4 different ways to set it up correctly. But after you cross multiply, we should all be at the same place. Okay? Distribute 2x cubed plus 2x squared minus 2 is equal to 3x cubed minus x. And actually, I wasn't thinking. I should have went the other way because I wanted my 3x cubed over there, but that's all right. No problem. So we definitely, our highest power is 3. And so factoring may be something that we can use here, and I'm going to try that. So I want to make this equal to 0, and factoring is all we got, so we're hoping that works, right? I'm going to subtract 2x cubed. I'm going to subtract 2x squared. I'm going to add 2, and that zeroes out the left side for me. On the right side, I'm going to have an x cubed, a minus 2x squared, minus x plus 2. And I have 4 terms. Remember, we got 5 different ways to factor. Only one of those 5 ways applied to 4 terms. Remember what we do with 4 terms? Factor by grouping. Okay. So we're hoping it works out. We're going to try it. The first group here, we could factor out a x squared. And the second group here, we could factor what out? A minus 1. We get x minus 2. Then we got one more step. Notice that both these terms have a common factor of what? So we factor out the x minus 2. You're left with x squared minus 1. You see any more factoring? Difference of 2 squares. X squared minus 1 can factor because that's a difference of 2 squares. Keep going. X plus 1 times x minus 1. And now it's fully factored. And so each factor will give you a different answer. Okay, so first one gives you x equals 2. Second one gives you x equals -1. And the last one gives you x equals 1. Do all of them make sense? None of them do. Okay, let's look at why. Let's look at the x equals 2 first. Why can't we have x equals 2? Okay. Yeah, so if you look at NL, you got an x minus 2. And if you plug a 2 in there, you get 2 minus 2 is 0. And so that one doesn't work for us. Why not -1? That would make, yeah, and actually NL is the one that kind of throws them all out, right? Because if you plug that in, you get NL being -3. And then if you plug the 1 in, you get 1 minus 2, which is negative. And so sometimes that happens. Sometimes that tells us that the picture right here is not possible. And so there's no solution. Okay. But there was valuable work here. Right? You're like, man, we did all that work to find that there's no solution. But here we set up a proportion correctly. Okay. We went through the factoring process, solved, and then checked our answers. So if we didn't have a context, we would have 3 answers. It would be 2, -1, and 1. We would keep those. But our context here is saying, hey, none of these answers make sense with this. And so we know that there's something in this diagram that is not possible. Okay. Let's try, let's just make sure we set up number 10 right. So go ahead and read number 10 and try to draw a diagram that would go with number 10. We're looking for some kind of picture like this, right? Like my fancy picture. I'm an artist on the, this is my second job here. So there's my tree, there's my 6-foot man, and there's the sun out and it's casting shadows, right? And so if you get this kind of picture and you can take it out of context and just draw kind of a triangle within a triangle, right? And you put some numbers in this diagram. Where would I put some numbers here? Right? To help you out here, I'll put A, B, C, D, and E. Where do I put a 6? So 6 here because he's standing 6 feet from the tree. What else can I put in this picture? 4 is BC because that his shadow is kind of on the ground here. So like he sees his head here and his hands are up here right here and he's matched to his feet or something like that, right? And then what else can we put in this picture? DB is also 6 because he's 6 feet tall, and we'll make this X because that's what we're solving for. And so that's the setup for 10. and then you would finish that, right? All right, I'm going to stop there and give you maybe 10 or so minutes to keep working through the homework problems, and then we'll start our next lesson.